Okay, we want to continue our work with integration. Here I have a more complicated integral to look at, the integral of 3x squared times the square root of 1 plus x cubed dx. I want to integrate this, and what I want to do is use a substitution, so I take this, make it look like this, and then apply this formula, which is a pretty easy formula to work with. So let me just show you what I'm going to do here. I'm going to say let's let u be equal to 1 plus x cubed. Now, because I have a little experience with this kind of integration, I know when I look at this right here, this looks to me like u to the 1/2 power. Everything else will kind of fall into place, but if I see this as u to the 1/2, then I'm thinking in terms of this formula right here. Let's see what happens. Well, if u is 1 plus x cubed, then when I differentiate, du dx is equal to 0 plus 3x squared. That's a pretty easy derivative to find. And now I'm going to think of this in terms of differentials. I know it's a derivative right here, but I've done this work with differentials, so I know I can think of these as two separate variables in a way. I'll multiply both sides by dx, and I'll end up with this. du is equal to 3x squared dx. Okay, well, if I look at this 3x squared dx, that looks like this right here, 3x squared dx. And if I look at my 1 plus x cubed, that's this right here. So this essentially, with this work that I've done here, makes this integral look like u to the 1/2 du. So I'm going to take all my work right here, I'm going to substitute it in, and what I'll end up with is the integral of u to the 1/2 du. And I've taken care of everything that's over here. Because u is 1 plus x cubed, this is u square root of u, which is u to the 1/2. Since du is equal to 3x squared dx, here's my 3x squared, here's my dx, that looks like du. So I've taken care of everything that's over here, and now I have this in the form of this, which is going to make it easy to integrate. So I'll just simply take that u, add 1 to the exponent, 1/2 plus 1 is 3/2, divide by 3/2, and then add on c. And that will be the antiderivative of this right here. My original problem is given to me in terms of x, so I would like my answer written in terms of x also. So I'm going to back substitute here and take this value I have for u, substitute it in here. Let me fix this up a little bit, 2/3 times u, which is 1 plus x cubed, all to the 3/2 plus c. Okay, so that's the answer to this problem. That's the integral of this right here. This is the antiderivative of this. So let's just go one step further here, and what I'm going to do is differentiate this so that I can prove to myself that I actually did this correctly. So let's take it up here and say, if y is equal to 2/3, 1 plus x cubed to the 3/2, plus c, then I differentiate and I get y prime is equal to, okay, there's my coefficient, 2/3, times, I take that exponent, multiply here, 3/2, times this base, 1 plus x cubed, to a power 1 less, 3/2 subtract 1 is going to be 1/2. And then remember, by the chain rule, I have to differentiate the base. The derivative of 1 plus x cubed is 3x squared. And then the derivative of c is equal to 0. So what do I end up with? Well, these multiply to give me 1. 1 plus x cubed to the 1/2 is square root 1 plus x cubed times 3x squared. So it turns out that this expression is the antiderivative of this expression, because if I differentiate this, I end up with this. So sure enough, the integral of 3x squared square root 1 plus x cubed dx turns out to be this thing right here, and I've just proved that by actually differentiating it. Okay, so that's integration by substitution. Let's try another problem. All right, here I have another integral to look at right here, log x to the 2nd power over x dx. Okay, well, when I see this, to me, it looks very similar to this right here, because I see I have a base, log x raised to the 2nd power, and the derivative of that base, the derivative of log x, is 1 over x dx. So it looks to me like it might be a good idea to just say let's let u be equal to log x, not log x to the second, but just log x, because I can take care of the exponent with my formula right here. So I'm just going to let u be equal to that base, log x. Then, when I differentiate du dx, I end up with 1 over x. All right, now I think of these as differentials, so that implies that du is 1 over x dx. And so it looks like with these two substitutions right here, u for log x, so I have u to the second, and then 1 over x dx, 1 over x dx can be du. I'll have this just in the right form. So I'll take these substitutions I have right here and rewrite this way. When I substitute this and this into this expression, I end up with the integral of u to the second du. Okay, pretty easy to integrate with this formula right here. So that just becomes u to the third over 3 plus c. I just add 1 to the exponent and divide by that same thing. Then I notice, my original problem here is written in terms of x, so I'd like my answer in terms of x. So instead of u, I'm going to write log x. So this is log x to the third, all divided by 3, plus c. So you see, fairly complicated looking expressions like this are fairly easy to integrate if they're kind of set up in the right form so that I can make this kind of substitution right here. Now, as you get better at this, you won't show this step right here. You just say u is equal to log x, du is 1 over x dx. That's fine. But, just to remind yourself, all you're doing right here is differentiating, and everything has to be set up so that this works. Does every substitution you try work? No, not every substitution you try works. Some things are set up in such a way that no substitution is going to work. But for the problems that you're going to practice here on your homework and that, you'll see that most of them they're set up so that there's a way to make the correct substitution and end up with an integral that's pretty easy to integrate. Trial and error sometimes, you don't always make the correct substitution the first time, but with a little practice you'll get better and better at this kind of integration.